Assalamu alaikum. In today's lecture, we shall talk about a phasor diagram of a real transformer. We shall also discuss voltage regulation. For the case of an ideal transformer, the primary and secondary voltages are related by turns ratio, that is Vp over Vs, that is equal to Np over Ns. That means that for an ideal transformer, if primary voltage is kept constant, the secondary voltage remains constant. No matter how much load is connected on the secondary side, if this voltage is kept constant, this secondary voltage remains constant. However, what happens in our real transformer is that the secondary voltage changes with changes in the load connected to the transformer. Here is the equivalent electrical circuit of a real transformer. For a real transformer, the secondary voltage changes with variation in the load connected on the secondary side. Even though if primary voltage is kept constant, the secondary voltage changes with variation in load connected to it. Therefore, for transformers, we define a term which is called voltage regulation. Voltage regulation is defined as the secondary voltage of the transformer when no load is connected on the secondary side minus the secondary voltage of the transformer when a rated load is connected to it, rated load also called the full load, divided by the secondary voltage at rated load. And if we are interested in percent regulation, voltage regulation, we multiply it by 100. So this voltage regulation gives us information about the performance of a transformer, that is how much variation is there in the secondary voltage with variation in the load. What do we ideally want is that we want no variation in the secondary voltage with variation in the load. That is, ideally we want the same voltage, secondary voltage at the no load and at the full load. That is, desired voltage regulation is we want it to be equal to 0. This expression can be equivalently written in this form as well. Voltage regulation at no load, if no load is connected to it, then this voltage, secondary voltage, is simply equal to, if we just ignore this current in the excitation branch, because this current is very small, it means that if this is open circuited, no current will be flowing through here, and this voltage will be equal to this voltage, and therefore this voltage and this voltage will be related by the turns ratio, that is Vp over A is the turn ratio, that is equal to Vs. So at no load, if we ignore this excitation current, the secondary voltage is simply equal to Vp over A. Therefore, voltage regulation is given by Vp over A minus Vs at full load divided by Vs at full load multiplied by 100. To further elaborate this point, let's consider the equivalent electrical circuit of a real transformer, refer to the secondary side, and then draw the phasor diagram. Here is the simplified equivalent electrical circuit of a real transformer with all quantities referred to secondary side. We have discussed this equivalent circuit in the last lecture. We have connected the rated load on the secondary side, and what we observe is that Vp over A, by applying the Kirchhoff's voltage law, this voltage is equal to this voltage plus voltage drop across this impedance, that is Vp over A is equal to Vs plus the current through the resistor is Is, R equivalent refer to secondary side, plus J Is and X equivalent refer to secondary side. So we sketch the phasor diagram for this equation, the secondary voltage can be represented by a phasor. This is taken as reference, the secondary voltage Vs. Let's first talk about the situation when we have connected an inductive load to the transformer. We shall also talk about other two situations, that is when we have connected resistive load and when we have connected a capacitive load. For the case of an inductive load, this current which is flowing through this inductive load will lag the voltage across this load. That is, the current Is, which is current through this load, will lag the voltage across this load. So Is current, secondary current, is given by this phasor. How to sketch this phasor? This R is a real number, so real number multiplied by this phasor will be just a scaling of this phasor. So this voltage is given by this phasor. R equivalent refer to secondary side multiplied by Is. This phasor is in phase with this phasor, represents this voltage. What is phasor representation of this voltage? This is a real number, so this quantity will be in phase with this one, and this J is an angle of 90 degree. So this voltage will be at an angle of 90 degrees to this phasor. That is this one. And Vp over A is phasor sum of these three voltages. That is, Vp over A is given by this phasor. This is phasor for Vp over A. What we observe is that the magnitude of Vp over A is always larger than Vs if we have connected an inductive load on the secondary side. That is, for the case of inductive load, this voltage regulation will always be positive. Vp over A is always greater than Vs at no load. So this voltage regulation of a transformer, when we have connected an inductive load on the secondary side, that will always be some positive number. What about a resistive load? We can easily draw the phasor diagram for a transformer when we have connected a resistive load to it. So let's draw it over here. Again, let's sketch the, let's take Vs as a reference. And now, since we have connected a resistive load, this current which flows through this resistive load will be in phase with the voltage across this load. So this is the phasor for the secondary current. We have connected the rated load, so rated current will be flowing. So let's call it full load or rated load. What is phasor for this one? R equivalent is a real number, so this phasor will be in phase with Is. So this is Is R equivalent refer to secondary side. Similarly, this phasor will be at 90 degree to the phasor for current, and this is J Is X equivalent refer to secondary side. And again, Vp over A is given by the phasor sum of these three phasors, and this is Vp over A. And what is voltage regulation for a resistive load? Again, for a resistive load, we can see that this Vp over A is larger in magnitude than Vs. So voltage regulation for a resistive load as well as for inductive load, that is greater than 0. For inductive and resistive loads, voltage regulation is always greater than 0. Now you can easily draw the situation for a capacitive load. So for a capacitive load, again we can sketch all these quantities. Here is the phasor for Vs at full load, and then for a capacitive load, current will lead the voltage. This current through this load will lead the voltage across the load. So here is the phasor for Vs. Phasor for this one will be in phase with this one. So here is the phasor for R equivalent referred to secondary side multiplied by Is. What will be phasor for this quantity? This will be at 90 degree to this phasor. That is this one. Here is Is, JIS, X equivalent referred to secondary side. And the phasor sum of these three quantities, that is this one, Vp over A, that will be equal to Vp over A. The phasor sum of these three quantities will be equal to Vp over A. So what is voltage regulation when we have connected a capacitive load to a transformer? So it will depending upon the current on the secondary side. It can either be, this length can be either larger than or even smaller than this length. So this voltage regulation for a capacitive load can be greater than 0, can also be less than 0 for a capacitive load. What is summary of all this discussion? Ideally, what we want is that we want no variation in the secondary voltage, even if the load connected to the transformer is varying. However, there is variation in the secondary voltage even if primary is kept constant with variation in the load. This variation is more significant when we have connected an inductive load. It is less significant when load is resistive, and it can be this voltage regulation can be either positive or negative when we have connected a capacitive load to our transformer. So since this variation in secondary voltage that is undesirable, so what they do in transformers is that they provide multiple taps on the secondary side. That is, on the secondary side they have multiple taps, and the effective number of turns can be changed by changing the tap. This is done online, and therefore variation in the secondary voltage is somehow avoided by changing the position of the tap. Effective number of turns can be changed, and hence the secondary is kept constant.